another, more subtle language that the universe speaks. A language. Gravitational waves are distortions in the very structure of space and time itself. They're created by some of the most violent and energetic events in the universe. Einstein's proposed that massive objects like stars and planets do not simply exist in space. They warp and curve it. This distortion is what we perceive as gravity. But Einstein went further. He suggested that when these massive objects accelerate, when they move, collide, or explode, gravitational waves are not just distortions in space-time, they also carry energy. When massive objects like black holes merge, they release an enormous amount of energy in the form of gravitational waves. This energy travels across the cosmos, rippling through space-time and revealing the most powerful events in the universe. Action by LIGO in 2015 confirmed that these waves carry energy away from their source, causing the black holes to spiral towards each other and eventually merge. The amount of energy carried by these waves is staggering. In just a fraction of a second, the merging black holes emitted more energy than all the stars in the observable universe combined. This discovery not only confirmed Einstein's theory, but also opened a new way to understand the most energetic processes in the universe, revealing information about the objects and events that created these waves. Each detection tells a story of the formation and evolution of black holes, neutron stars, and even entire galaxies. The energy carried by gravitational waves does more than just stretch space. It allows us to map the universe's most extreme environments, to understand how black holes and neutron stars form, and to explore the very nature of space and time. Gravitational waves not only affect the space they move through, they also have profound effects on the very objects that create them. When two massive objects like black holes merge, the gravitational waves they emit carry away significant amounts of energy. This loss of energy directly impacts the motion and structure of the black holes themselves. When neutron stars collide, the effects are even more dramatic. Gravitational waves not only strip away energy, but also determine the final outcome of the collision. Whether a new, more massive neutron star is formed or whether the stars collapse into a black hole. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater accuracy. When a gravitational wave passes through Earth, it arrives at each observatory at slightly different times. By measuring these time differences, we can pinpoint the source of the waves in the sky. The global network has enabled us to conduct multi-messenger astronomy, where gravitational waves are observed alongside light, radio waves, and gamma rays. Together, they paint a fuller picture of the great attractor on our galaxy and the challenges scientists face in observing this elusive region of the cosmos. We'll also travel to the recently discovered South Pole Wall, a vast cluster of galaxies stretching at least 700 million light-years into space, and its intriguing connection to the great attractor. So, will we eventually be consumed by this anomaly, or does it still serve another purpose in the grand scheme of the universe? Let's find out. About 4 decades ago, astronomers used the Parkes telescope, but we cannot see it directly because it's located in the avoidance zone, a region of space hidden by the dust and stars of the Milky Way. Despite these challenges, scientists have made significant progress in studying the great attractor. They have used various techniques, such as X-ray, infrared and radio observations to peer through the dust and gas of the Milky Way and gain insight into this mysterious region of space. According to information to date, the Great Attractor is part of a larger structure called the Norma Cluster, which is one of the most saturated known galaxy clusters. It is in this cluster that the center of the Great Attractor is located. The Norma Cluster is moving toward the Great Attractor at an astounding speed of about 1,340 miles per second. So as we've said, the gravitational influence of the Great Attractor extends over a region of space spanning hundreds of millions of light years. This hides part of the universe from our view. But with the help of advanced technology and innovative techniques, we've been able to peek behind this veil and see hidden galaxies. The use of infrared surveys has been crucial. These surveys have allowed us to confirm the presence of galaxies that were previously hidden. It's like having a torch that can illuminate the dark corners of the universe. An equally tantalizing aspect of Ganymede lies beneath its icy surface. Scientists believe there is a vast ocean of liquid water beneath the ice, containing more water than all of the Earth's oceans combined. Zeus, known as Jupiter in Roman mythology, took a beautiful mortal boy to become the cupbearer of the gods. This boy's name was Ganymede. It seems appropriate that the moon carries such a large amount of water around Jupiter. But perhaps the most intriguing feature of Ganymede is something we can't see. It's the only moon in our solar system that generates its own magnetic field, a trait usually reserved for planets. This magnetic field creates beautiful auroras in Ganymede's rarefied atmosphere, a sight truly worth seeing. The question arises, could this distant, icy world harbor the conditions necessary for life? Our understanding of Ganymede has been greatly enhanced by the daring missions sent to the Jupiter system. Kneading is done by Jupiter's gravitational pull. As Ganymede rotates around Jupiter, the planet's gravity attracts different parts of the moon with different forces, causing it to bend and stretch. This bending and stretching creates friction within Ganymede, and as with dough, the friction generates heat. This heat could be enough to melt part of Ganymede's interior, creating a layer of liquid metal that would generate the moon's magnetic field. Among other things, Ganymede's magnetic field is unique in that, unlike Earth's, it's embedded in Jupiter's powerful magnetosphere, creating a complex and dynamic electromagnetic environment. This magnetic field is important for the potential habitability of Ganymede. It creates a magnetosphere around Ganymede that could theoretically protect life on the moon from harmful solar radiation. In addition, the interaction between Ganymede's magnetic field and Jupiter's magnetosphere produces auroras in Ganymede's thin atmosphere. These auroras have provided scientists with valuable information about the internal structure of Ganymede, for example, confirming the presence of an ocean beneath its surface. More recently, the Juno spacecraft has been studying Jupiter, similar to the plumes observed on Saturn's satellite Enceladus and possibly Jupiter's satellite Europa. Incidentally, we've already debated whether there is life on Europa in another video. Similarly, while the existence of subsurface ocean on Ganymede is supported by several lines of evidence, the exact properties of this ocean, such as depth, composition, ability to harbor life, all still the subject of ongoing research and debate. Despite these challenges, our quest to explore Ganymede and other distant worlds continue. Each challenge we overcome brings us one step closer to understanding our place in the universe. As we traveled through the mysteries of Ganymede, it became apparent that our exploration of this fascinating satellite is far from over. Now, general relativity. If we summarize this theory in one sentence, its main idea is that gravity is a curvature of space, not a force that acts on all objects, and the laws of physics apply equally everywhere. But what does this have to do with light? According to GR, light is constant. That is, it always has the same speed and is probably the fastest phenomenon of all. The reasons for this are the absence of mass of photons. Moreover, since light has no mass, it's not affected by gravity. However, if it passes near a black hole or a star, or more precisely along the geodesic lines of space-time near a massive body, its path and energy consumption increase and curve, but its speed remains constant. So if the speed of light is constant and photons are not affected by time, especially in space, 7 and its jet, a beam of ionized matter ejected from galaxies at high speed. A group of researchers took several pictures of the jet. They noticed that the jet seemed to be moving faster than light. However, this is probably just an optical illusion caused by photons that were emitted later from almost the end of the jet. So it seems to us the light from it travels a shorter distance. Moreover, there's another phenomenon in space that can accelerate particles to the speed of light, but this time it is true: magnetic explosions. When magnetic fields collide with each other, they can often become entangled. If the tension between them increases greatly, they will break apart, which will throw all the charged particles away in an ultra-high speed. This process can be considered a natural particle accelerator. However, this is all about measurements in a vacuum. Recall that light travels through a certain medium, such as water, more slowly than in a vacuum. When a particle moves faster than light in some medium, it polarizes other particles, or in other words, it repels or attracts. When the charged particle moves further, the electrons are returned, which causes the butte glow of the irradiation. One hypothetical subatomic particle could be another competitor to light in speed. In 1962, scientists considered the possibility of the existence of particles that would be faster than light with the inclusion of GR. But in their work, they noted that such particles could move faster than light from the moment of their appearance and not by increasing their speed, which is not contrary to GR. These theoretical particles were called tachyons. Unlike other particles, a tachyon has energy, but its mass at rest is imaginary, meaning it has a mass only when moving faster than light. It's also likely that an approaching tachyon will be invisible because light travels slower than it. In particular, it's also hypothesized to speed up when it loses energy. It's believed that a tachyon is formed when energetically strong cosmic rays hit the Earth's atmosphere. So far, the existence of tachyons has not been confirmed, and therefore light can be considered the speed limit at the moment. In addition, tachyons can lead to logical temporal paradoxes. For multiple observers, a tachyon can travel to the future and the past. So, if a tachyon can travel back in time, this leads to the classic causal paradox, for example, in which a traveler can affect his own existence and prevent his own birth or send a message to himself in the past. However, does superfast motion really lead to traveling back in time? In fact, faster-than-light travel is not necessarily the cause of paradoxes. For one observer, a spacecraft whose speed exceeds the light constant will travel back in time, so it will also land in the past before it took off. However, according to the physicist Sabine Hossenfelder, such paradoxes are possible from the standpoint of special relativity, not GR. Thus, another observer, for example, can move along with matter in the same direction, forward in time, which means that the ship for him moves only forward, and therefore cannot break the causal relationship and first land and then only take off. In fact, the second observer follows the entire process, and therefore does not see any logical violations that arrive from the perspective of the first observer, who believes that the ship is moving backward. So we can't simply accelerate to the speed of light. However, we know that light travels in space-time. What if we could bend space so that light travels a longer way than the object around which space is deformed? It sounds fantastic, but scientists are considering this space travel option. This concept is called the Alcubierre drive or warp drive. The idea of a warp drive is to stretch the canvas of space into a wave which should hypothetically compress the space in front of an object, such as a ship, and expand the space behind it. Thus, the ship will essentially move on this wave in a so-called warp bubble faster than light. Alcubierre's drive consists of three parts: the inner bubble or passenger space, where time passes more slowly than in the general space, and two outer parts, a shell of negative and positive energy and normal space without changes. However, warp drive requires a conceptual negative energy, which is impossible according to GR, but can exist in quantum theory in small quantities. This is one of the main problems of this theory. So to be able to implement it, it is desirable to find a method using positive energy. In 2021, astrophysicist Eric Lentz was able to develop such a concept. According to his model, such a bubble should contain a liquid plasma with a huge mass, about 10% of solar energy, and electromagnetic fields that would be located around the ship in the shape of diamonds. Such a bubble would be able to transport the ship, but only at a speed close to the constant of light, meaning that such a drive would not be able to accelerate to FTL. So far, it's impossible to confirm whether warp drive can exist without negative energy, as well as to start experimental work on it in general. However, if warp drive can work without the use of negative energy, then in the future, we'll be able to travel to distant planets much faster than with current technology. Another way that negative energy could hypothetically allow us to travel in time actually faster than light is through Einstein-Rosen bridges or wormholes. Einstein first came up with the idea of the existence of such tunnels from one place in space to another. It's believed that wormholes can be connected at gigantic distances of several million light years. However, although they have not yet been found, wormholes are very unstable, so they can quickly disappear due to negative energy. In addition, they're probably not as wide as we imagine. Also, because of this energy, wormholes must be small for a person to pass through. Therefore, until scientists find a way to keep both wormholes stable and large enough to confirm their existence, we cannot use this method for travel. Finally, quantum physics offers an interesting hypothetical way to transmit information at speeds greater than the light constant. This method of FTL communication is called quantum entanglement. In fact, quantum entanglement is an inseparable combination of two quanta that can exchange information with each other faster than light despite the distance. Particles communicate by changing their state, for example, by changing their spin or energy. So during a long-distance travel in space, hypothetically, an astronaut could send a signal about possible life on the exoplanet under study, and this signal would reach the controller almost instantly. However, in reality, it is their variability and randomness that's the main problem that makes this concept of FTL information exchange unlikely. Quanta cannot be brought into a certain state to transmit any data because then the particles will break the connection with each other, and the particle whose state has not changed would show random results. So communication in this way would be impossible and probably not even reach the speed of light, because information cannot be transmitted at a speed greater than the light constant according to quantum mechanics. Moving at the speed of light or even faster gives us a serious advantage in space exploration. At the moment, we're not able to achieve this speed, but the hypothetical ideas of warp drive and tachyons, as well as the use of knowledge about FTL in different environments, can be an important step towards further research into ways to achieve the light constant. However, this is still in the distant future, so our priority now is to develop the technical knowledge we have so that our main goal in the study of space-time will be speed. In the vast expanse of space, among the countless stars twinkling in the night sky, celestial events of unimaginable scale and power take place. Events eclipse entire galaxies and reverberate throughout the universe. Today we will delve into one such event, the stellar cataclysm known as the universe. Supernovae have always fascinated us. Journey to understand these stellar cataclysms and their impact on our planet and their story of our place in the cosmos. We dive into the fascinating world of supernovae. In the great theater of the cosmos, the stars are the protagonist. They are born, they live, and they die. But some stars give such a spectacular performance in their final act that it outshines entire galaxies. They are supernovae, the catastrophic death of stars. But what is a supernova? Simply put, a supernova is a powerful and bright stellar explosion. It occurs during the last stages of a star's life, when the nuclear fusion in its core can no longer support the outer layers of the star. Supernovae are not just fascinating cosmic phenomena. They play a crucial role in shaping the universe. They are responsible for the distribution of elements throughout space, elements necessary for the part of a star that was cut short by a spectacular explosion. Of new stars, which we now know as supernovae. One of the earliest recorded observations of a supernova was supernova, and its remnants, known as RCW 86, have been observed with modern telescopes. Another famous historical supernova is SN 1054, Crab Nebula. Today we continue to study supernovae not as omens but as opportunity to learn more about the life cycle of stars, the creation of the elements, and the history of our universe. Although our understanding of the cosmos has grown, these stellar explosions continue to fascinate us with their power. It may soon become a supernova. However, it has since returned to its normal brightness. The most widely accepted explanation for this event is that the star emitted a large dust cloud, which obscured some of its light and made it dimmer from our perspective on Earth. When the dust cloud dispersed, Betelgeuse's brightness returned to normal. This serves to remind us the universe is not a static place, but a place where stars are born, live, and die in spectacular ways. Every star in the night is a mere cloud of gas and dust to a beacon of light that can outshine a galaxy. The journey begins in nebula, a huge cloud of gas and dust. Inside these cosmic nurseries, pockets of gas and dust begin to collapse under their own gravity. When they collapse, they heat up and form a protostar. Over millions of years, the protostar continues to gather mass from the surrounding nebula. As it grows, the pressure and temperatures in its core increase. When the core temperature reaches about 27 million degrees Fahrenheit, nuclear fusion begins. The protostar is now a main sequence star, just like our Sun. A star can remain on the main sequence, burning hydrogen in its core for billions of years. But eventually the hydrogen fuel runs out. What happens next depends on the star's mass. In stars the size of our Sun, the core shrinks and heats up, causing the outer layer to expand. The star becomes a red giant. Eventually the core collapses and the outer layers are ejected, forming a planetary nebula. This leaves a white dwarf. But as we travel through space, we find that not all stars meet their end in the same way. A star can also go supernova. Its type will largely be determined by the mass and composition of the original star, while also having its own unique characteristics. For example, famous subtype, type Ia, occurs in a binary stellar system. A white dwarf, the dense remnant of a star similar to our Sun, sucks matter from its companion star. Once the white dwarf reaches a critical mass, it undergoes a thermonuclear explosion, resulting in a supernova. On the other hand, type Ib and IcC, helium. Now let's focus on one of the most common types of supernovae we observe, type 2. These supernovae originate from the massive stars much larger than our own Sun. Stars with at least 8 times the mass of the Sun can undergo this dramatic transformation. Throughout their lives, these massive stars are in a constant battle between gravity pulling inward and the force of fusion pushing outward. When a star exhausts its nuclear fuel, gravity wins the battle. The core of the star collapses under its enormous gravity. This collapse of the nucleus occurs incredibly quickly, in just a fraction of a second, and leads to a powerful explosion, a supernova. The outer layers of the star explode in a spectacular spectacle, outshining the entire galaxy for a short time. What's left of the star may form a dense neutron star, or if it was massive enough, a black hole. But the legacy of the star lives on. The explosion disperses the elements formed during the life of the star into space, seeding the cosmos with building blocks for new stars, planets, and even life. When a star goes supernova, it's not just a spectacle of light. It's one of the most energetic events in the universe. The amount of energy released in a supernova explosion is so enormous, it's equivalent to the energy the sun would radiate over its entire 10 billion year lifetime. But where does all this energy go? Most of it is carried away by neutrinos. These tiny, nearly massless particles are produced in huge quantity during a supernova. They travel at nearly the speed of light. The rest of the energy is released as light and other forms of electromagnetic radiation. This includes gamma rays, the most energetic form of light, and X-rays, which are less energetic but still much more powerful than the light we see. The visible light from a supernova is so bright that it can briefly obscure the entire galaxy. This light can be seen at great distances, making supernovae important cosmic beacons for astronomers. Although supernovae are interesting to observe, they can also pose a potential danger. The enormous energy and radiation released in a supernova explosion can have significant consequences, especially if the supernova is close enough to Earth. One of the main causes of concern is the impact. In addition to gamma rays, the supernova also emits a stream of high-energy cosmic rays. These particles can further damage the ozone layer as well as create streams of secondary particles in the Earth's atmosphere that would increase the radiation dose. In our study of the dangers posed by supernovae, there's another interesting aspect to consider: gravitational waves. These are ripples in the fabric of space-time caused by some of the most violent and energetic processes. Massive accelerating objects like a neutron star or a black hole orbiting each other would collapse space-time in such a way that distorted space waves would emanate from the source. And supernovae, with their incredible mass and explosive energy, are the first candidates to create gravitational waves rippling through space. These waves will be incredibly weak by the time they reach us and will pose no danger to Earth, but they give us a new way to study the universe. Scientists have already begun to detect these waves with incredibly sensitive instruments, ushering in a new era of gravitational wave astronomy. Fortunately, the probability of a supernova exploding close enough to affect Earth is quite small, but understanding these potential dangers is crucial. It's a reminder of our connection to the cosmos and how events occurring light years away can have consequences right here on our home planet. As we've seen, supernova explosions are powerful events that can have far-reaching consequences. But did you ever guess that supernovae may have played a role in shaping Earth's history? Correspond to the pulsation patterns of the star, in particular the radial principal mode and the first, second, and third overtones. This observations and analysis aimed at deciphering the secrets of this distant star. The researchers' findings lead to an exciting conclusion. Betelgeuse could be the next star in the galaxy to go supernova. Given the current study also notes that the star's high rotation rate as a red supergiant has sparked discussions about its evolution, including the possibility of past mergers with another star as a source of angular momentum. However, it is important to note that predicting exactly when a star will go supernova is extremely difficult because it depends on many factors that are not fully understood. Even if a star has indications that it might go supernova, it could be thousands or even millions of years before it actually goes supernova. But rest assured, when it does, it will be a grand spectacle. The study of supernovae is crucial to our understanding of the universe. These stellar cataclysms are not only endpoints, but also